Hello everyone, this is Ed. Today I'm gonna go through a LeetCode challenge problem with you called populating the next right pointers in each node. So this question is pulled from the most common interview questions list on LeetCode. So it's a good one to know, especially if you're struggling with trees and the different algorithms used to traverse trees. Alright, so you are given a perfect binary tree where all leaves are on the same level and each parent has 2 children. The binary tree has the following definition. And each entity on the tree is called a node. Each node has a value, a pointer, which is like a relationship to another node, a relationship to the right node, and a pointer called next, which we're going to learn. Okay, populate each next pointer to point to its next right node. If there is no next right node, the next pointer should be set to null. Okay, so let's look at these pictures for some clarification. So this is a perfect binary tree. A binary tree is one in which each node has a left and right branch. This is a perfect one because the last row of the tree is fully populated. So all the nodes, all the leaves are on the same level. The leaves are the last nodes of a tree on the last row. Okay, so what does it mean? What is the next pointer? The next pointer is the node that is to the right of a node, right? So 1 doesn't have any nodes to its right, so its next pointer is set to null. On level 2, node 2 has node 3 to its right, so its next pointer is set to 3. 3's is set to null. So that's basically this problem just wants you to find the node to the right of a node, right? Okay, so to do this we're going to have to figure out a smart way of traversing the tree such that it's easy to find out which nodes are next to each other. So let's draw from a real-life example here. Domino's, not the pizza chain. The game, Domino's game. Let's see. Yep. Knock over. Okay, so when you press the first domino, there's going to be a chain of events, right? All the dominoes following it are going to fall. So why do we care? Because dominoes are fun. No, but it's really, it's actually a pretty accurate description of this problem. So imagine these are dominoes, right? And they're kind of stacked up like our tree examples on LeetCode. Okay, so I'm adding the branches from each parent domino to the baby dominoes. Okay, let's use a less aggressive color, like green. Okay, so this is the root domino. It's going to set everything in motion. I'm going to number these the same way they're numbered in Leet. Sorry, I can barely fit these numbers in here. It's no space. Okay. So when you knock over the root domino, there's going to be a wave of dominoes falling, right? Each row of dominoes are going to fall in succession. So it's going to be 1, then it's going to be 2, 3, and 4 to 7, right? And imagine there is a way to traverse this such that we could get it in this order. If we do that, it's really easy to just iterate through each row and set the next pointer from the previous node to the adjacent node. Well, good news. There is a way to do this, and it's called breadth first search, also abbreviated and commonly known as BFS. So let me give you a quick rundown of BFS. BFS uses a data structure called a queue. So the definition of queue is a line, right? A queue is basically a line, like the annoying lines you have to wait in to, get a seat at a very popular restaurant, or to get into a very to wait for gas at Costco. So there's a rule in lines where it's first come first serve, right? If you cut in line, you're breaking the rules, and everyone's gonna get angry at you. Okay, so we're going to process these. We're going to imagine each of these rows right here as a queue, right? So this is one queue, this is two queue, this is three queues, right? We need a while loop to iterate through these rows, right? So this is going to be our first iteration of the loop, second, and third. Okay, so in our first iteration is going to contain the root node. That's going to be the constant, right? We're always going to start with the root node. That's what we're given in each problem. So I'm going to do some magic here and teleport this domino into our queue. Unfortunately, our queue is not big enough, but I can fix that. Just let me expand the queue. There we go. Crap. Okay. Okay, so we're going to add the root node first. This is the only node in this row, so the queue is only going to contain one element. So now we want to iterate through this queue, right? We're going to iterate through it, and we are going to set a node, the previous node, to its current node. Previous node is going to be initialized to null. Now you can't set a null's next pointer, otherwise you're going to get null exception error, right? So we're going to check, hey, if there is no previous node, don't set it. Since it's initialized to null, and we haven't set it yet, the next pointer is not going to be set. And remember, by default, every node's next pointer is set to null. So we don't even have to do anything. Okay, so let's just leave this rule hanging here, and everything's good. Okay, what else do we have to do to process this node? Well, we're going to want to add the elements of our next row. So we're going to look at the left and right children of root. So left and right. And we're going to add it to a temporary queue. Oh no! Oh man. Just starting to get proud of my beautiful masterpiece. I just messed up. So this is a temp queue that's going to store the next row of nodes. So our root node is connected to 2 and 3. So you probably can guess that our queue is going to be a magnitude of 2 bigger, right? Because we are multiplying the number of nodes in our previous row by 2, since each node has 2 siblings. Children. So our temporary queue is right here. And what happens when we're done iterating, done processing each node? Well, simply dispose of the node. And we will put the contents of temporary queue into queue to prepare for the next iteration. So now temporary queue is ready for the next row. In this case, it's the third row of nodes, right? So I'm going to mark a node as processed by writing it in black, right? So 1 has been processed and it's done its job. It's it's set all its next pointers and it's added all its children nodes to our queue. So now we're going to iterate through these dominoes in a similar fashion, starting with domino 2. Okay, so we're going to check. Is previous node null? Okay, if it's null, then we don't set a next pointer, right? So for the first iteration of this loop where we're going through the dominoes, we're not going to set a next pointer. But we do add the left and right nodes to our temporary queue. So we're going to add 4 and 5. So I really don't want it to copy over there. Okay, but I don't know. It's doing it. Okay, so we're going to add its children to the temporary queue. And at the end of the iteration, we're also going to set previous node equal to the current node. So in this case, the current node is 2. So this is preparing for the next iteration where we can set the previous node to 3, right? So we have completed this iteration. Let's cross it out. So now we are here. Let's get rid of this. Okay, so first we're going to set the previous node next node pointer to the current node. So we set it as 2. So we're going to set this, set its next pointer to 3. And we're going to add the children of 3 to our temporary queue. In this case, it's 6 and 7. And there we go. Okay, we're done iterating through this queue. So 3's next pointer is going to be the default, which is null, right? And remember, at the end of, when we're done iterating through a row, we are going to swap the queue's contents for the temporary queues. So we're going to substitute the next row. We're going to start with the next row, right? We have finished this row. We finished processing. Okay, we finished setting the next pointers, and let's do the last row together. Okay, so the last row has 4 and 5, so there are no children to add, so the temporary queue is going to be empty. But in similar fashion as last time, we're going to set the previous node to the current node until we get to the last element. After we're done with that, we're going to remove everything in here and basically put nothing in. And we know when we're done because the size of the queue is 0. That means we processed everything, including the leave nodes. And basically, all you have to do is return the root node, and that's the answer. Okay, hope you learned something. Subscribe, like, or comment. Thanks. Bye.